Yeah, my name is Oriach. I'm the head of R&D in Monocrom, and I'm presenting this paper on behalf of my team. Special thanks to the big efforts performed by Eduard Carbonell and Claudia Garcia on that. So while I was studying quite a lot of years ago, I was told by one of my professors that when you do an oral presentation, it's important to kiss the audience. KISS standing for keep it short and simple. So I tried to prepare a very short presentation, just summarizing the results that we got on these experiments. I will go firstly through a brief company and technology introduction to explain a little bit what is this solderless technology that we use to mount the laser bars. We will review also the experimental setup being used in this work in order to move to the presentation of the results and discussion to reach finally the conclusions. Monocrom is a company that was founded back in the year 93 in Barcelona. We are still based there. It's a family-owned company employing 50 people. And we basically do laser modules. So essentially, this slide represents almost 90% of our business. So we do laser bar stacks. We purchase the semiconductor. We are not doing semiconductor, but we do the packaging. We produce all our electrodes or heat sinks, you name it. Out of these laser diode stacks and arrays, we produce, of course, some laser diode models, just combining with optics, mechanics, cooling, fibers if needed, whatever our customers may need. We can also arrange them in the form of gain models. So doing side pumping of solid-state crystals, mostly neodymium YAG and neodymium ILF. These gain models can be used either as oscillators or amplifiers. And out of that, and also from some end pumping schemes, we have a line of solid-state lasers. Again, essentially YAG and ILF based in the fundamental and down to the third harmonic. So the very core of all this, as you can see, it's essentially the laser bar stacks. All the rest of the products are based on that. And here's where we have quite a different way of packaging the laser bars that I think that deserves a certain introduction to explain a little bit what we are doing. So normal technologies in the market for mounting laser bars are presented in the first two columns here. Everyone most probably knows them. Soft soldering is a pretty old technology where the laser bar is bonded normally P-side down to a copper heatsink by means of an indium foil, while the end side is either wire bonded or from time to time you can see also some copper foils connecting the end side there. This technology has essentially one nice advantage and one nice disadvantage. It has a very low thermal resistance because of the materials involved, but at the same time the CTE mismatch causes some problems. You have to heat up the assembly up to a bit more than 180 degrees in order to get the indium melt and solder the assembly. So at the end, when this temperature goes back to the normal operating temperatures, let's say 20-25 degrees, the CTE mismatch creates what's called the smile effect on these samples. At its turn also, when you hard pulse this stuff, you had some fatigue effect, so thermally induced mechanical fatigue effect. So a second technology to mount laser bars, which is also very well known and that overcomes essentially the problems of the CTE mismatch, is the hard soldering technique. In this case, the laser bar is bonded via gold tin soldering on a on a substrate, on a copper tungsten substrate, which essentially matches the CTEs, the gallium arsenide here, the gold tin here, and the copper tungsten here. And then this at its turn is soldered onto the normal copper heatsink. As the CTEs here are all the same, you can avoid quite a lot, to a very nice extent, the smile effect, although you introduce then some extra thermal resistances. More layers of material means, well, more contact resistance, and on top of that, copper tungsten has a lower thermal conductivity than pure copper, so you gain from one side, you have some losses from the other side. So the way we mount, it's pretty naive in terms of number of components. We just take the laser bar, we process the electrodes in a certain way, that's why we produce all our electrodes ourselves. And we can essentially mount the laser bar clamped between two copper electrodes. So by means of this technology, we still have a very high CTE mismatch, but we are agnostic to that because we do that at room temperature. We mount at 23 degrees. So there is no further contraction of the elements. And then the main question that we had here is whether we have a good or not thermal resistance. So we have less materials, which is good, but at the same time we do not have a thermal interface material, which could be thought to be bad. So essentially we wanted to analyze the thermal resistance of our mounts. By the way, just to show how this CTE mismatch is not a problem anymore in the clamped bars, this is the kind of smile that we can achieve in laser bars. We are regularly achieving a smile below 0.3 microns peak to valley, whatever bar we mount. Normally, and paying a bit of attention on all the process, we can reach down to 0.1 microns peak to valley. This is essentially really, really good. So although we have this CTE mismatch, we do not care about it that much. So the question was, okay, what are we doing to the thermal resistance? In order to answer that, we went down to all the several components that affect thermal resistance in a simple formula. At the end of the day, we decided we had to study how we are affecting the threshold current by pressing the laser bar, how are we affecting the slope efficiency and voltage drop. So overall, we are talking about electro-optical efficiency, but at the same time, we wanted to know whether we have any effect on the wavelength tuning coefficient or thermal characteristic. It has several different names, but it's essentially how the wavelength of the laser diode varies over temperature, right? So in order to do that, we designed a quite simple experiment at the end of the day. We chose to work with a normal CS mount because this is quite kind of a standard in the industry, so a lot of people could reproduce the experiments on their sites, even with soldered laser bars, where we have a thermistor well here. And essentially, our technology allowed us to vary the pressure by two means. We have what we call the preload bolt here, and then we assembled the CS mount on top of a Peltier cooler. And by means of this kind of bridge, we were also varying the load directly on the laser bar. And we basically had two different setups, really simple, one integrating a sphere for pulsed measurements in order to check the wavelength variation over temperature, and a second setup for CW operation so we could get the LIV curves, seeing the voltage and optical power out of that. So moving a bit forward, we had firstly to test whether we were doing good when trying to measure this wavelength temperature coefficient. And first thing we did was essentially we took commercial laser bar, 808 nanometer, 40 watt, 19 meters, 30% fill factor, operating it at 0.1% duty cycle, and we checked whether we were introducing some self-heating while operating the bar this way. How did we check that though? So we basically chose two different operating modes, 5 hertz to 100 microseconds, 1 hertz, 1 millisecond, same current, 40 amps, and check whether the slope of this experiment was equivalent, was the same. This is what we have here. We have in red one operating mode, in gray the second operating mode. We see that the curves are perfectly parallel. So this is indicating that at least the difference between these two operating modes is not creating self-heating. And at the same time, well, second test that we did was essentially when we decided to work at 5 hertz to 100 microseconds, we checked two different current levels, 40 amps and 10 amps, just to see whether this slope varied a lot or not. We can certainly see a certain slope variation, but it's really low when compared to the values that we got afterwards, because these curves represented something quite surprising for us. But before moving to the numbers that we got, I would also like to explain that we had to test whether all our mechanical setup was in an elastic regime or inelastic regime. It is important to be in the elastic regime in order to know that we are not deforming anything and the results can be repeated several times. So here we are presenting different changes in the load and the preload factors. So first we basically varied the preload volt, creating a pressure on the laser bar from 11 megapascals to 28 down to 11 again, and repeat the curves. And we can see that there is a slight difference here in the second curve than the one we had in the first one, but essentially the performance is the same. And when having a fixed preload at 28 megapascals, which is the maximum we got, and varying the load volt from 0 to 17 and down to 0 again, we got these two curves before and after, which are perfectly parallel, meaning that the setup is working in the elastic regime, which was quite important for us. So now moving to the results we got. I basically want you to explain that we used two different bars. The one I already introduced. We used another one because everything is gallium arsenide based, but the concentrations might be different. So we wanted to check whether our results were repeatable with different laser bars, and it was not something related intrinsically to that specific laser bar. So these are the two kind of laser bars that we used. One important remark here is that we tested the elastic regime up to the maximum forces we could apply, meaning that the pressure that we will see in the graphs when we present bar type 1 or bar type 2 are essentially 1/4 one of the other because of the surface. Okay, another important remark that we had to do here. We wanted to study the effect of the mounting of stress directly, meaning that we wanted to avoid components that were not in the plane of the p-n junction, stress components that were not there. For that, it is important to start with laser bars that have a natural bending when they are unmounted, which is rather low, right? So that's another reason to why did we choose these two laser bars. These are the bowings that we got in these two types of laser bars. We have seen things that are way beyond that, and we prefer to focus on things that are already pretty flat, let's say, in order to start with. That way we can ensure that the strain is perfectly on the plane of the p-n junction, because we are doing the force on the 001. We are applying the force in this direction, 001 crystalline plane. So one thing that we tested here, and I told at the beginning, how the electrical filters change with the pressure in these laser bars. And we essentially measured threshold current changes, slope efficiency, and series resistance changes. Having these kind of results, as you can see in the first column, the threshold current is increasing with pressure. Here we have three different serial numbers of the same laser bar, right? So it's essentially increasing always, which is normally thought as being a negative effect because the electro-optical efficiency would be reduced by that. But at the same time, the slope efficiency increases, which is good, and the series resistance is reducing, which is also good in terms of electro-optical efficiency at the end of the day. So this is how the electrical filters behave, essentially. But the most surprising results came not from here, but from the wavelength tuning coefficient. And we are presenting them here, especially those results that we got from bar type 1. As you can see here, we are showing, variations over temperature of the wavelength in steps of 1 degree. The measurements were done waiting for a stabilization to a point better than 0.1 degrees. And here you can see essentially how we are increasing the load and then the slopes change. It's quite clear that the higher the pressure, the higher the slope here, meaning that the temperature coefficient is increasing. This happens in both types of bars, although here is not super clear, not really noticeable that the gray line corresponds to 16.7 megapascals when compared to 2.8 megapascals of the red one, and you see the increase here. Here the pressures are way higher, the variations. This is one kind of strange effect, but here we see two more strange effects. First of all, the slope is not constant at all. At least for this bar type. Here is quite constant, but here is not. Here we have this kind of kinks over 50 or 60 degrees. This kind of behavior was even reported a couple of years ago by Vlasova in red laser diodes, but counteracting, so that the slope here is decreasing in this point in the temperature while they saw an increase. Most probably the semiconductor being different explains that. And here, this region here, when the load is really high, like for example the gray squares here, there's a big jump. And this is repeatable in all the laser bars in 808 that we have tested, which was quite a big surprise for us. And honestly speaking, we do not have a very clear explanation for that. So we know that pressure effects creates a degeneration in the balance band. It could be that heavy holes and light holes at this temperature can have some changes between them, and the transitions go from one kind of level to the other. But we are not 100% sure about that. So at the end, okay, we are presenting here the curves, but what about, what is the real wavelength versus temperature coefficient? This is what we want to show here. Again, for the two types of bars, and different serial numbers plotted, but you normally take for 808 nanometer a rule of thumb, they are moving, or the wavelength tuning coefficient is 0.27 nanometer per Kelvin, is here, and we saw that with increasing pressure, the wavelength tuning is essentially going higher and higher. This was honestly kind of a surprise for us. These kind of results also repeats here. I see that I made a mistake with the axis. It should reach 0.25, and we would see that the line for 910 material is at 0.3. So what we can see is essentially that the wavelength tuning coefficient, when submitted to these high pressures, or somehow high pressures, mounting pressures, it's increasing up to 40%. And this has, of course, a consequence afterwards when one is measuring the thermal resistance, which is what we are summarizing here. When measuring the thermal resistance, and these graphs might be a bit misleading, so they need a certain explanation. Here we see, we wanted to plot here together the thermal resistance together with the wavelength tuning coefficient and the electro-optical efficiency, just to show that, and everything in the same scales, to see that, for example, here, this line here represents the electro-optical efficiency of this laser bar, being 55 to 60%. The green line represents the temperature tuning coefficient, so the variations that we saw are not that big when put in this scale, but the thermal resistance reduces quite a lot, more than one could explain from the behavior of the electro-optical efficiency and the temperature tuning coefficient. Similarly, for the bar type 2, the thermal resistance is getting low and low, just again remarking that the pressures that we can apply to these laser bars are lower, 1/4 of what the ones we can apply to 1 millimeter bars, but the behavior is essentially the same. So the thermal resistance is reducing, while this thermal resistance reduction cannot be explained either by an improvement or a variation in the electro-optical efficiency here, or the wavelength tuning coefficient here. So essentially, what this is telling us is that by pressing the laser bar, we are improving the thermal contact between the laser bar and the heatsink. And we would remark that the values achieved here for the thermal resistance are quite pretty impressive for a CS mount. I mean, and provided the bars that we are using. This is a 10% fill factor bar, so just 10 emitters, 100 microns each, while this is a 30% fill factor bar. So, and I will go again to these numbers in a couple of slides, but before that, I would like to show how this reflects to the performance of the laser bar after all. I'm just plotting here the highest and lowest pressures that we have applied, just for sake of clarity, not having a lot of lines here, a typical LIV curve, showing the power on the left and the electro-optical efficiency here for these two different pressures, 5.6 and 16.7 megapascals. This is on the 4 millimeter laser bus. So we can see that the electro-optical efficiency is affected and effectively increased from 63 to 65%. Here we saw that there started to be a certain thermal rollover, meaning that, yeah, clearly the thermal contact is improved, and you can also see it here. In this graph here, we are just showing the waste heat and the delta temperature. We had a heatsink temperature of 20 degrees, and this would be the junction temperature of the laser bar increase above this 20 degrees. So, well, the pressure can change the junction temperature easily 5 to 10 degrees at operation point, 70 watts of waste heat, which is basically generated at 100 amperes for these laser bars, close to that. So really this pressure mount improves quite a lot thermal resistance when compared to the standards in the market. Last but not least, we wanted to check how close are we from an ideal thermal contact, having no thermal interface material in between. So we went for some thermal simulations in finite element analysis. So the model of the laser bar is pretty simple. In this case, we are modeling here the 19-emitter laser bar, 30% fill factor, so you can essentially see the heat flow that was introduced on each emitter. And on the left side, we have the temperatures. I'm not sure they can clearly be seen here in terms of resolution, but this is indicating highest temperature to hit 32 Celsius, and the lowest temperature emitter would be something at 28. Just consider that when we measure the temperature of the laser bar, we are making an average of all those emitters. We measure the temperature 29.7. Another remark regarding the approximation, an approximation that we used here is that we have the emitters in direct contact with the heatsink, which is not real. You also have, the metallization. You have a bit more material in there, but measurement and reality are in pretty good agreement when you use a perfect thermal contact in the model between the laser bar and the heatsink. So overall, I will just summarize a little bit what we have found here, and it has been a bit surprising for us, is that the temperature tuning, the wavelength tuning coefficient with temperature increases dramatically by pressure, which was completely unexpected. We have seen some kinks in the 808 material that are not clearly explainable right now, and they are not appearing in the 910 material. And at the end, also that this pressure mount, this clamping that we call this clamping mount, reduces a lot the thermal resistance of the mounted diode bars without having problems with the CDE mismatch. So, reached to this point, I would like to thank you for your attention. I'm open for questions.